All right, let's start this mechanisms of aldehydes and ketones with two fundamental different approaches to forming a hydrate, one in acid and one in base. So we can tell the difference between the types of mechanisms that happen in acid versus base. So when you're in acid, you tend to not have as strong a nucleophile, but you do have acid that can activate the electrophile. You have acid that can protonate the oxygen of the carbonyl. So let's go ahead and have that happen. We have the electrons attack the proton, forming the protonated aldehyde or ketone, but here we have an aldehyde. So the positive charge on this oxygen is causing it to pull more electrons away from the carbon, making this carbon even more electron poor, more electrophilic, and more subject to attack, even by water, which is a weaker nucleophile than hydroxide for sure. But we can have water come in here and relieve the electron, the positive charge on this oxygen. So the result is a positive charge on the incoming oxygen, which now has 3 bonds. This oxygen now has 2 bonds and 2 lone pairs. And then the last thing that has to happen is the loss of a proton to give the normal hydrate. And so this is our product, the normal hydrate. The other product is a proton. So the proton that we used at the beginning is catalytic. It's regenerated at the end. We are only adding H2O to the aldehyde to make the hydrate. And I've drawn it with the OH at the bottom because that's where I brought it in from, but you could draw it more normally with the 2 OHs next to each other if you like. When we are in base, we should not be adding a proton to the aldehyde because we do not have a lot of protons around if we are in base. However, we could have some hydroxide ion around. So we can show hydroxide attacking the aldehyde. This will make a negatively charged intermediate. So in opposed to the positively charged intermediate that you have in acid, you have a negatively charged intermediate in base. This can then grab a proton from a water molecule nearby. And so we have the hydrate again. This time we've regenerated the hydroxide, so the hydroxide that we needed at the beginning to do the attack. Now we have another one. So again, we have just catalytic base forming the hydrate. So this next one uses a ketone. For a lot of these mechanisms, I'm just doing either the ketone or the aldehyde, but the other one can be done, like the hydrate we've seen above, could be done on a ketone instead of an aldehyde. This hemiacetal could be done on an aldehyde instead of a ketone. So if we are in base, we need to generate an alkoxide ion in order to attack the ketone. We're not going to be able to protonate the ketone. Then we'll go ahead and show that negatively charged oxygen attacking the ketone, making a negatively charged intermediate. Then for the final step, that negatively charged intermediate needs to grab a proton from somewhere. You could have grab a proton from water and regenerate the hydroxide. You can have it grab a proton from another alcohol to start the cycle again, so that next alkoxide can attack a different ketone. So here the side product that I've generated is another alkoxide ready to attack the next ketone, and we have this hemiacetal intermediate. Now the next thing that would have to happen to form a full acetal is protonating this oxygen over here, but since we are in base that can't happen, and so we can only have the hemiacetal if we're in base. If we're in acid, we can create the full acetal. So the first step in acid is to activate the ketone to attack by protonating it, making it more electron poor. Now we can have an alcohol come in and attack. I've gone ahead and drawn the alcohol on the side rather than on the bottom because I need it to be closer to do the next step. I'm having a proton transfer from this oxygen that just came in to the oxygen that we want to leave. So now we have water as a leaving group. We can have these protons go to that carbon and kick out the water. So water has been kicked out. That's the side product. The other product is this ketone, I guess, that is positively charged. The other alcohol is nearby, so that lone pair can add and relieve the positive charge on that oxygen. So now we pretty much have an acetal, just that this proton is still here. So we'll have that proton leave, and that gives us the full acetal. We also have the proton regenerated, the same proton that we started with, another proton. So it's catalytic. We regenerate a proton. We don't consume acid in the process. So for this next one, for cyanohydrin formation, we are not in strong enough acid to protonate the aldehyde or ketone. If we were in strong enough acid to protonate the aldehyde or ketone, then all of our hydrocyanic acid would be protonated. We wouldn't have any cyanide ion to attack. So unlike water, when you have acidic conditions, you don't have hydroxide around, but the water itself does not need to be negatively charged. It does not need to be hydroxide because the oxygen has a lone pair that can do the attack. If you have hydrocyanic acid, the carbon does not have a lone pair that can do the attack. So to do the attack, you do need to have the negatively charged cyanide ion. So you can't have super strong acid, otherwise none of this would be around. So we are going to attack with the cyanide ion. But then on the other hand, once you form this negatively charged oxygen, we do need to get a proton from somewhere. So we do need to have the pH such so that you might have some of the hydrocyanic acid around so that this oxygen can grab a proton and regenerate cyanide ion that can then do the next attack. I'm just going to go ahead and draw the cyanohydrin without the hydrogen here. I just won't draw it. It's still there. Just this looks more like the product that I drew up above. Cyanide ion has been regenerated to attack the next aldehyde that comes along. So the different conditions that I've seen, you can have sodium cyanide with a trace amount of acid, or sometimes you see the conditions over the arrow as HCN with a trace amount of hydroxide. You're just adjusting the pH so that you have both cyanide ion and a little bit of hydrocyanic acid. So it's fairly neutral conditions. So this next one I believe we've seen before. Let's just go ahead and do that again. For a reduction with sodium borohydride or lithium aluminum hydride, you can just draw the hydride ion as attacking. There probably is some complexing going on between the oxygen and the aluminum, especially in this case. Aluminum likes to be next to oxygen. You might see it some places drawn that way. But it is okay to just simplify it and show the hydride ion, which is negatively charged hydrogen, has a lone pair of electrons attacking. Remember, you can never show a proton attacking, but you can show hydride attacking because hydride is a nucleophile. So that creates a negative charge on the oxygen, which again is probably complex to aluminum or boron. So in our reaction mixture, we would have sort of aluminum salts of these products, and then when you work up with water, that's when that oxygen can then get a proton back. You could take it from water, I guess, to make this match the reaction conditions that I have given you. I'll go ahead and put this as acid, because I said I had H3O+. And since this was an aldehyde, the product is a primary alcohol here. So this is a very similar mechanism to other negatively charged nucleophiles adding to a carbonyl. This time I have a ketone. with Grignard, which is effectively a negatively charged ethyl piece here. Here we have a negatively charged propyne. I guess I'm using the drawing over here this time. We're having this negative charge attack the ketone. So this carbon over here had 2 carbons on one side, 3 carbons on the other. The piece that came in has 2 carbons. Those are the 3 pieces that are now attached. And this would exist as a magnesium salt at first. And then when you add water or slightly acidic water to the reaction flask at the end of the reaction, that's when this would get protonated, giving the tertiary alcohol in this case. I wanted to point out that in your text, figure 19.6, it actually emphasizes the fact that the magnesium is complex to the oxygen. So it shows the magnesium attaching to the oxygen first, making the oxygen extra reactive, and then it brings in the Grignard, the carbonyl, the negatively charged carbon, the carbanion part of the Grignard reagent. So if you wanted to do that, if you wanted to show the oxygen complex to magnesium, you could do that. Again, this is the magnesium salt that you have in the reaction flask before you do the water workup at the end of the reaction, and so then it would get a proton from water. So you could show it either way. I didn't actually show the magnesium complex to the oxygen, I just showed the oxygen being negative. That's another option as well. Here, I didn't even say what the counter ion to the carbon anion was. It's probably sodium, so if you want to have sodium hanging around next to your oxygen for this next one, you can. It's not really necessary. We're just going to show the negatively charged carbon. I think I'll draw the actual carbon here. So we have a 3 carbon piece. The terminal alkyne carbon is the one that has been deprotonated, so it only has 3 bonds and a lone pair, giving it a negative charge. Since I didn't leave a lot of room on these pages, I'll go ahead and use the drawing itself for the attack. And here we have our tetrahedral carbon. It had a 2 carbon piece and a 3 carbon piece to begin with. It also has a bond to oxygen. It used to be a double bond, now it's a single bond. And then 1, 2, 3 carbons got added. The carbon that has a triple bond is directly connected to the carbon that got attacked. And then this needs a water workup of some sort. This proton would not be around during the actual attack because it would protonate this carbon anion first. So this is a second step, and that creates a tertiary alcohol as well. All right, so let's show an amine adding to a ketone to make an imine. Again, this is something that can be done on an aldehyde as well. We have to be kind of careful about the pH here, because if you have too much acid around, the amine will be protonated and it won't be able to attack the ketone on its first step. So we're not going to show the ketone being protonated because that would be too acidic an environment. The amine would be protonated before the ketone would, and then it would not be able to attack. So we'll go ahead and show the amine attacking. That temporarily creates a situation where we have a positive nitrogen and a negative oxygen. We can fix that pretty quickly, having that proton transfer to the oxygen. So now we have both of these atoms being neutral, but in order for the OH group to leave, which is what we want to happen, we do need to have that protonated. You can show a proton going onto the oxygen. That's what your textbook shows, by some acid somewhere. Again, we don't have that much acid around, so another thing you could do is just show this grabbing this proton while it leaves. So this proton needs to leave the nitrogen so that the nitrogen can form a double bond to carbon. And then you could show these electrons grabbing the hydrogen, or you could show these going back onto the oxygen and a lone pair grabbing the hydrogen or the proton at this point. So if we show all of this happening in one step, that gives our water molecule and the neutral imine in one step. I'll show it in 2 steps if in case you've seen it that way other places. So you may have seen oxygen grabbing a proton in a separate step here. Let's go ahead and draw this up here. And then now that we have such an excellent leaving group as the protonated oxygen, this would definitely kick the OH group out, leading to this protonated imine. Having this positively charged oxygen here just does not seem like it would be realistic in trace acid. If you wanted to, instead of drawing this intermediate, you could also show as the oxygen grabs a proton, have this lone pair go down, and so that would bring you directly to this protonated imine. The previous mechanism I showed avoided the protonated imine altogether because the oxygen grabbed this proton here. So instead we have it grabbing a proton from the solvent somewhere else in the system, which is fine. Then we have this protonated imine here, and then we have the proton falling off of the imine, just giving the regular imine product. Your textbook actually shows the proton over here coming from H3O+. I think it's very unlikely that with trace acid we would have H3O+. More likely we would have some protonated amine around instead. So it probably would be best just to show the proton on its own or show the proton attached to the nitrogen. Between water and an amine, any protons that are around would definitely be attached to the amine, not to the water molecule, because the amine is much more basic. So it's more realistic to show this as your proton source, or just show H+ as your proton, or as I showed at first, you could just show it you could just draw it showing the oxygen taking this particular proton instead, so that you get it in one step. All right, so let's go ahead and show a secondary amine adding to a ketone instead of a primary. So this time you will make an enamine instead of an imine. The initial step is the same. We have the nitrogen attacking the ketone. It can also happen to an aldehyde. We're not showing the protonation of the ketone first. I'm going to use some of this screen over here. But we're not showing the protonation of the ketone first because that would be too much acid around. The amine would then be protonated and it would not be able to attack. So no doubt that resolves itself fairly quickly. The negative oxygen taking the proton from the positive nitrogen. Oops, I lost some carbons over here. So now we have this neutral intermediate. In order for the OH group to leave, it should probably be protonated. This time I'm going to try having it happen in one step. So we'll have this lone pair on the nitrogen come in and kick out the oxygen, and we'll have the oxygen use this pair of electrons to grab the proton as it's leaving rather than protonating it and then kicking it out. We'll just have it grab the proton as it's leaving. You could show that in 2 steps if you want. Protonate the oxygen first and then kick it out like we did previously. So here is our water molecule that left. Let's draw it further away. So we have successfully kicked out a water molecule. The nitrogen is now positively charged. The difference is that we cannot get rid of the positive charge on this nitrogen like we did last time by taking off a proton. It does not have a proton. The 4 bonds are all to carbon. And so this has to lose a proton from a neighboring atom. So the proton that falls off is not on the nitrogen. It is on a neighboring carbon. So we'll go ahead and show that proton falling off. The electrons go to form a double bond to carbon, and then these electrons can go to being the lone pair on the nitrogen. So now we have a neutral nitrogen atom with a lone pair, and we have a double bond to a neighboring carbon. So we have an enamine instead of an imine. All right, so I had to clear some space to be able to show this next mechanism. Your textbook just lets you know that the hydrolysis of an imine is the reverse of forming an imine, but let's go ahead and work through that. Okay, so for most of our imine mechanisms. We're showing the proton falling off of the nitrogen as the last step. So we'll go ahead and show the proton going on the nitrogen for the first step here. We're going to have attack by water. We are in acid, so we don't have hydroxide around, so we'll show the water attacking and the pi bond going onto the nitrogen as a lone pair. All right, so now we have a positively charged oxygen, a neutral nitrogen. We're trying to get the nitrogen to leave. We're trying to make this the aldehyde. So let's go ahead and show the proton transfer. We'll put the proton on the nitrogen instead. So now we have the lone pair on the oxygen that can come down and form a pi bond to the carbon, kicking out the nitrogen. So then we have the protonated aldehyde product. We can show the proton falling off. We could also show this amine grabbing the proton. If we're in acid, then probably any amine that gets hydrolyzed off is going to be protonated, making this reaction more difficult to go in the reverse direction. So we'll go ahead and show that. So we have our aldehyde product, and if we are in acid, then the amine that we hydrolyze off is probably the ammonium ion instead. So let's go ahead and show this similar thing happening to an enamine. So I had this drawn in the note packet by accident. It should be, if you have an enamine, it's because the amine coming in was secondary. So instead, I don't even have a primary amine because I don't have a hydrogen here. I think I just forgot to draw this second alkyl group. I have a nitrogen with just 2 bonds here. This is a incorrect way to draw nitrogen. So let's go ahead and use a proper enamine where the nitrogen does not have a proton. It has 2 alkyl groups on it, and that it is next to a carbon-carbon double bond. So let's use that as our enamine that we're going to hydrolyze. I will redraw it here properly. So if you remember from forming an enamine, the last thing that we had in enamine formation was, instead of a loss of a proton by nitrogen, we have a loss of a proton from a carbon. So instead of protonating the nitrogen, we're going to go ahead and protonate the carbon so that we can have the reverse of the enamine formation. So we'll go ahead and draw this pi bond, this lone pair forming a pi bond, and this alkene getting protonated. And that gives us this nitrogen ion. It's better than just protonating the nitrogen, because if you protonate the nitrogen, then there's not much that can happen there. If you protonate the carbon and put the positive charge on the nitrogen and the double bond to the nitrogen, now we have something where this water can come in and attack the carbon that we need it to attack in order to form our ketone product that we are going to get. So now we can have water come in and attack. That gives us this intermediate. The nitrogen can go ahead and grab the proton from the oxygen. Now the nitrogen has a positive charge instead of the oxygen having that. So we can kick the amine off as a leaving group here. So that kicks off the amine, leaving a protonated ketone. The proton would definitely rather be on the amine than on the ketone. The amine is much more basic. So then our main product would be the ketone, and then the amine in acid would be the ammonium ion. So we have dimethyl ammonium and cyclohexanone as the 2 products there. All right, let's show the Wolff-Kishner reduction of a ketone, which is somewhat related to this imine formation. It, according to your textbook, has the first step as form the hydrazone in the normal way. So let's go ahead and draw what that looks like. So we'll have this nitrogen come in and attack the oxygen. So again, that results in a negative oxygen and a positive nitrogen. We need a proton transfer to fix that. All right, so we are in base. So I don't want to go ahead and show too many positively charged intermediates here. So we're not going to protonate the oxygen to make it leave. We'll go ahead and just sort of take a proton from the nitrogen and kick out. We can either kick out hydroxide, or we can show the oxygen taking a proton from another water molecule, making more hydroxide. If you form the hydrazone first in like a more acidic conditions, you can draw it a different way, but since we're forming it in this in the context of the Wolff-Kishner and we're in base, we'll go ahead and keep to basic conditions. So we'll go ahead and extract this proton from the nitrogen so that we just form the neutral hydrazone rather than one with a positive charge. And if we're in base with a lot of hydroxide around, we probably could kick out hydroxide, but if you want to kick out a water molecule, you can. Let's not lose the rest of our chain here. So we showed a lot of solvent molecules taking part in that step. Now we have the neutral hydrazone and we have some water. We still have some hydroxide. So we're cooking this up in hydroxide conditions here. Let's go ahead and draw out these hydrogens because we're going to have some base deprotonate the nitrogen next. And then that causes the double bond to migrate to being between the nitrogens. Your textbook shows this with the negative charge just kind of landing on this carbon atom, but that probably wouldn't last very long having that carbon ion, so I'm just going to have that immediately grab a proton over here. But you can check out your textbook if you want to see the negative charge landing on the carbon first, and then they have a second step where that negatively charged carbon grabs a proton. We'll just go ahead and do this in one step for now here. So I didn't actually draw out the hydrogen that this carbon grabbed. You can if you want to. So this carbon now, it did not used to have a hydrogen. It used to have 2 bonds to nitrogen, 1 to this carbon and 1 to that carbon. Now it has 1 bond to nitrogen and 1 bond to a hydrogen that it grabbed from the water. Let's go ahead and repeat that process a second time. We'll have a hydroxide come in and grab this proton from the nitrogen. This now forms a triple bond between the 2 nitrogens. And then again, your textbook shows this double bond as landing on the carbon and making a carbon ion. Instead, I'm going to have it just go ahead and grab a proton instead of doing that in 2 steps. The negatively charged carbon, I'll just show immediately grabbing a proton here. So then the results that you get from that, you have a water, you still have hydroxide around. So each of these steps you have a water and a hydroxide, and then at the end you have a water and a hydroxide, so that's catalytic base there. The other thing that you have is nitrogen triple bonded to a nitrogen, otherwise known as nitrogen gas, N2. So that is the structure of nitrogen gas bubbling off there. And then the carbon now has 2 protons, and it has been reduced from a ketone to an alkane. So let me clear a little space to do this last mechanism, addition to a beta carbon. Let me go ahead and point out that a very minor contributor to this structure is one where there's a partial negative charge on the oxygen and a positive charge on the beta carbon. So the beta carbon is electrophilic, similar to how a regular ketone has a very minor contributor of positively charged carbon here. This is why we say that carbon of a carbonyl is electron poor, because we have a very small amount of this taking place where the pi bond is being kind of pulled onto that oxygen. So you can imagine if there is a alkene here, so if there were an alkene here, this would be an allylic cation, so the cation would be partly here at this carbonyl carbon and partly here at the beta carbon. So we could show that over here, that these electrons can get pulled over here and these can get pulled over here, creating this resonance structure. It's not a major contributor, mostly we have this, but it is a minor contributor. So we're just showing that this alpha carbon, or no, sorry, this is not the alpha carbon, this is the alpha carbon. The carbonyl carbon and the beta carbon are both partially positive. They're both electron poor. The alpha carbon is not electron poor. The alpha carbon does not have a positive charge in any of these resonance contributors, but we have these 2 possible sites of attack.
So there are certain nucleophiles that prefer to attack the carbonyl carbon itself when you have an alpha beta unsaturated system like this, and there are other nucleophiles that prefer to attack the beta carbon. So this amine is one of the ones listed that prefers attacking the beta carbon. Let's show that. So here we have the intermediate. We need to have a proton transfer here because this nitrogen doesn't really want to be positive. Also, the oxygen doesn't particularly want to be negative. So we'll have the ketone reform its bond. This pi bond, we can show it grabbing a proton from somewhere else and also show this proton falling off, but I will just show it grabbing this particular proton. So we have reformed our ketone. There is no longer a double bond between the two carbons. This carbon now has two hydrogens on it because it got one of the protons from nitrogen. So here is your textbook showing the difference between addition to the carbonyl carbon, which would form the imine, and addition to the beta carbon, which would form the product we just drew earlier. And so since additions can be happening and it's kind of equilibrium, so the nitrogen can fall on and off of the carbonyl carbon, and it can fall on and off of the beta carbon. This product is more stable, so it forms that. Earlier on in the chapter, this is all in section 19.13, we just have I like how they have the drawings right next to each other, that they have a nucleophile adding to the carbonyl carbon itself, forming some of the products that we see, like a Grignard would form this kind of alcohol product, versus having a 1,4 addition. So we have a 1,2 addition where the double bond counting, the two atoms that react are right next to each other. That's what the 1,2 addition means, that you have these just two atoms involved, basically. When you have a system of the alpha beta unsaturation, you can have 4 atoms involved, so that could be a 1,4 addition. If you only involve the 2 atoms, like for a Grignard, even despite the fact that this alkene is here, it would still be called a 1,2 addition. But if you involve the whole system, then that's a 1,4 addition. When the nucleophile adds in, it puts the negative charge partly on the oxygen, partly on the alpha carbon. So they're sharing this negative charge here. Here are the resonance structures. And then when this gains a proton, when this negatively charged intermediate gains a proton, it would preferentially gain the proton on the carbon, reforming the ketone. A carbon-oxygen double bond is pretty strong, pretty energetically favored. So instead of the enol, which is what would happen if you put the proton here, you would get the enol form. For most structures, the ketone form is favored. Or it could be an aldehyde if this over here is an H. So these lines, if one of these lines leads to an H, that's a similar pattern for the aldehyde as for the ketone.